Good evening, good morning, good afternoon, everyone. My name is Budiman Minasny. I am here in Sydney. I'm from the University of Sydney. It's very exciting to host this first scientific webinar from the 4/1000. And the topic of today's presentation or webinar is on the soil carbon saturation. But before we begin, I would like to first welcome Paul Lu. Paul Lu is the Executive Secretary of the 4/1000. He'll like to welcome you and give you a brief introduction about our program 4/1000. And by the way, I'm a member of the 4/1000 Scientific and Technical Committee. Over to you, Paul.
Hello. Hello to everyone. Thank you very much, Budi. I'm very glad to welcome you for this third webinar organized by the Scientific and Technical Committee of the 4/1000 initiative. This is the first, and we hope that it will be a long series of webinars organized by the member of the STC. And thanks to Budiman for this initiative that was accepted by the group of the STC at the last meeting. To begin with, allow me to say a few words about the 4/1000 initiative, which is, as you probably already know, an international initiative that came into being at the COP21 in Paris on December 2015, and whose aim is to promote carbon sequestration in soil to help combat climate change and improve food security. From the 160 partners that led to the creation of the initiative, we have now grown to nearly 780 countries, international organizations, scientific institutions, producer organizations, NGOs, and businesses. Since 2020, the initiative whose governance is based on the Partners Forum, the Members Consortium, the Scientific and Technical Committee, and the Executive Secretariat, that means 4 bodies, has had a 2050 strategic plan, grouping together 24 operational objectives, the implementation of which is based on working groups, and projects. The Scientific and Technical Committee of the initiative, which was set in November 2016 during COP22 in Marrakesh, comprises 14 renowned scientists with complementary scientific skills related to carbon storage in agriculture and forest soil from the 5 regions of the world and with equal gender representation. At his 14th meeting in Helsinki last June, as I said before, the STC decided to organize a series of webinars to address topics related to the scientific world and the objective of the 4/1000 initiative. Today, is the first webinar on soil carbon saturation. But I think I will let Budiman develop more this idea, and I will let the speaker take the floor. I would like to thank you very much, all of you, to participate to this webinar, and particularly the speaker and the member of the STC. Have a good webinar, and we will be delighted to continue this series and continue the work in order to fight climate change using soils and soil health carbon sequestration at first. Thank you very much. Have a good webinar.
Thanks, Paul. Thanks for the introduction. Our first speaker is Professor Francesca Cotrufo. Francesca is a soil ecologist and biogeochemist, and she's a professor at Colorado State Universities. She has degrees from University of Naples and Lancaster University, and her expertise is in soil organic matter dynamics, and she uses isotopic methods to study the processes, and her aim is to understand the mechanism behind soil organic matter formation and its responses to global environmental changes. She also dedicates in promoting soil health and mitigating climate change through innovative soil testing and management practices. And she serves as an editor for Global Change Biology and has received several awards for her contribution to soil science. Dr. Cotrufo is committed to research, education, and outreach to address humanity's impacts on the Earth system and sustainable solutions. And she recently found a soil carbon solution center at Colorado State University. So over to you, Francesca.
Thank you, Budiman and Paul. I mean, it's amazing that you guys arranged this this webinar with so many invitees that the room is full. It's really a testimony to the importance of the subject, but also to the importance of discussing and debating to advance knowledge. So that's I think that's really a big kudos for you to organizing this. So yes, I like basically to share my ideas about why I think that from a physical standpoint, mineral-associated organic carbon saturation is a robust concept, but indeed we have a lot of knowledge gap, and we should focus and clarify what they are and focus on them to move forward. So why do I think that carbon saturation is a robust concept? It's basically physics, right? We need mineral surfaces to accumulate organic carbon. The mineral surfaces in soil are finite, and therefore it is a foundational physics phenomenon that at some point we are expected to saturate the capacity of these mineral surfaces to accumulate carbon. But we need to be careful with what we call mineral-associated organic carbon, and that's what I'll be finishing off, because of course, if we start piling up organic carbon associated to carbon bonded to mineral, then I would doubt the stability of this additional carbon, and I would be careful to call it stabilized mineral-associated organic carbon. So the fact that this is a robust phenomenon is seen over and over by the strong relationship between clay and silt content and their reactivity in soils, and the amount of carbon that we find associated to this fraction of soils. This is one of the latest syntheses. There are other on the way, but also you know, a global scale, we see that there is always a relationship that can vary on a number of things. Here, Kati Georgia demonstrated the dependency on the activity. We are doing other analysis where it seems to be dependent on moisture, on cultivation, but there is always this relationship. And this is a global synthesis, but has been found over and over again from the very initial analysis that we all know of Assings, and then revisited and by the classic paper from 16 et al. Has been found at the national scale in France, at New Zealand, and this is the work we are currently doing in North America using the NICS soil. So this relationship is robust, is always been found. And so what I really like to stress today is that debating is amazing, it's very important, that's how we advance science, but let's debate on the real things. So I think negating the physical concept of MAOC saturation is actually unproductive. It's not the right question to ask in my mind. But there are a ton of open questions regarding saturation that we should ask, and we should work together to address them. So, of course, the first one is, what is the capacity? You know, what is that limit? When is reached? When is relevant? The other thing that we want to really stress, because, for example, that's what we observed in Europe, is that the large majority of soil actually reach steady state before capacity. And that is very relevant and very important to carbon sequestration, and we should understand why is that. Finally, for the soils that are close to capacity, we need to understand how that affects their rate of further acquisition, but also the rate of loss of carbon, because we can, you know, we want, with the 4 per mill and other initiative, accumulate carbon in soil, but we want to accumulate carbon that persists in soil. And so we need to be careful with how much the carbon that is accumulated close to saturation is actually not stable. And that links to what I was saying before, that often with the current method we quantify as MAOC actually organic carbon associated to MAOC, and that might not be stable or even contaminate the MAOC with other organic carbon. So I will now go to this point. First of all, what is the upper limit? Now, Georgiou actually found a limit that is similar to FANG. Again, those are global analysis, which vary, of course, on the amount and reactivity on the clay and silt in the soils. And so the more the clay and silt, the more you can accumulate. But the other thing I wanted to point your attention is that we are talking of an handful of soils that go past 50. The large majority of them are actually below that thing. So yeah, there are some soils that could accumulate more carbon, but are those the ones we need to focus on? Maybe as a potential, maybe understanding them why they accumulate so much. But the large majority actually is below 50. The other thing that I want to point your attention to is that if we, instead than presenting the mineral associated organic carbon per gram of soil, we do it in relation to the amount of mineral of the mineral associated fraction, then what we found is that actually only at the low silt and clay carbon content, so only coarse soils have very have the silt and clay fraction highly enriched with carbon, and with fine soil we often don't see this. And so again, the saturation is an issue mostly for the low for the coarse soils, coarse textured soils. But I would say that if the theoric saturation is an issue, it's more important to understand why actually even natural soil don't reach that saturation point. Why do we see that a lot of soils stabilize and reach steady state without making their capacity? And here, Cathy Stewart pointed to the native capacity, but actually I would say that that's a theoretical capacity. Even natural soils often are found below the capacity, and that's what we found in Europe, where basically we sampled soils that were representing of the variability of soils in Europe. So we didn't go and fish for those few soils that behave differently. We extracted a representative sample of the European soils. And what we observed in this paper, where we were actually not studying saturation, but different behavior of the MAOM and POM fraction, what we observed that only the MAOM actually appear to reach a steady state, which if we take Cathy Georgiou as the maximum capacity at 80 or something like there, you would say that actually most soil stabilize much below their potential. And so if there are a handful of soil up here that we haven't collected, that might well be. But to me, the point is why that happened for the vast majority of soils. And I would, this is a study that a student of mine, Paige Jansen, is now has under review in Global Change. I would point to the fact that, yes, as I started, the texture is a significant controller of MAOC accumulation, which is also a global analysis that used Georgiou point, but also many more. But actually, MAOC is also highly controlled directly by precipitation and by input. But even those three controlled together, they only make a small. They only explain a small component of the variability in MAOC. And so to me, the real question is, what controls the fact that we see a steady state in MAOC that is largely below saturation? That's the question we need to answer if we want to increase carbon sequestration across the majority of soils on Earth. But also the other thing, if we negate carbon saturation, we start doing a disservice for the farmers and the producers that have soils that are actually coarse textured, and they are likely to be close to saturation. And so their ability to accrue carbon is much smaller, hasn't been demonstrated with data, than for systems that have a high capacity, maybe again finer textured soil. And so in my mind, negating saturation does miscommunicate an important concept to producers with coarse textured soil that should do management to maybe increase capacity, maybe increase structure, rather than just increasing input if they are close to saturation. And the other thing is the reverse issue. Instead, if soils are close to saturation, adding more carbon there actually increase the potential for that carbon to be lost to the environment with climate change. So again, we don't do a good service and negating saturation if we then end up suggesting that we can pile up as much carbon as we want on this mineral fraction, because actually that additional carbon might well be very vulnerable to losses, as has been demonstrated in this study by Mayer and in several others. And that's where I come to the foundational issue that we really still don't understand well, also because we can only go at these questions with nanosims or with very specific finer scale analysis, and we are not able still to do this analysis at large scale on this global to continental data sets. And that is, what is the difference between organic matter that bond to organic matter actually bonded to minerals? Can we call all of that stabilized? Are the methods that we are currently using really separating the stable organic matter, or a lot of it is actually organic carbon associated to MAOC? And the other issue is not just that, it's also organic matter that contaminates the sample. And so, for example, this is a study that a student of mine, Sam Leufeld, has done and is under review, is that particularly for the POM, these are the exact same 12 agricultural soils. If we separate them by size or density, the POM specifically, we get, this is FTIR spectra, we get a very different fingerprint. But even the MAM, if we separate size from density, the size is by far more contaminated with the POM. So we need to really be careful in what we are separating. And that is, in synthesis, like, let's not negate saturation. Let's understand it better. Let's see where it's relevant. Inform the farmer, depending on their texture and their soils, what should they do to accrue carbon and to accrue stable carbon. And let's find a method to really measure the stable mineral-associated organic matter. And let me end with a joke, because like when we want to, in this debate, it's fun to say, I'm from Naples, I had to end with this joke, right? So, I was saying that the availability of dough doesn't determine how much toppings we can put on a pizza, or is it the stability of the sauce the same as the stability of all these toppings? So that's the choice of the conversation. Thank you very much.
Thank you, Francesca. So before we go to the next speaker, if you have any questions, please put it in the chat box, and we will go through it later. So our next speaker is Dr. Christopher Poeplau. Christopher is a senior researcher at the Thünen Institute of Climate Smart Agriculture in Braunschweig, Germany. And his primary interest is on soil organic matter dynamics and related it to biogeochemical processes. Christopher's academic journey began with his studies as applied environmental sciences at the University of Trier, and then followed by a study in advanced GIS at the University of Kiel. And early in his career, he also worked as a freelancer in geology. So later he embarked in a PhD in the Thünen Institute of Climate Smart Agriculture. And then after completing his doctorate, he had a postdoc position at Swedish University of Agriculture in Uppsala. And then after that, he returned to Germany and resumed his research at the Thünen Institute of Climate Smart Agriculture. Christopher also in parallel have a expertise as a lecturer at the University of Hildesheim, specializing in geography. And in 2018, Christopher also obtained his habilitation from University of Hildesheim and earning a Venia Legendi for physical geography and geoecology. And he currently leads the soil monitoring group at the Thünen Institute of Climate Smart Agriculture. And I hand over to you, Christopher.
Okay, so yeah, really excited to be here today. Thanks a lot, Budiman, for organizing this webinar, and also thanks to the initiative, and thanks to Francesca for the beginning. So my name is Christopher Poeplau, as already introduced, and I'm at the Thünen Institute, and together with my colleagues, who I'd like to acknowledge first, Neha, Henrike, our PhD students, and Axel Don. We've been discussing these topics and yeah, researching it for quite a while. And many of you have seen this paper that Francesca already kind of mentioned, that we didn't find a detectable upper limit of mineral-associated organic carbon in agricultural soils, not directly stating that there is no saturation, because it is a physical concept, but we're not observing it. So let me start. So soil organic carbon accrual is very beneficial for soils. We know that it can help to mitigate climate change. It is important for multiple soil functions, soil fertility, and from a farmer's perspective, it can even earn money, either directly nowadays or in the long term, because it really adds value to your land. At the same time, SOC accrual is also costly and limited. And these four things that I mentioned here are probably worth to organize a webinar for them in themselves. So you first need a lot of biomass, that's for sure, and this biomass could also be used for other things. You need a lot of nutrients, so soil organic matter finally has a relatively low CN ratio. You need to, in some measures, spare some land, or at least compromise maybe some food production, and you might even get some additional greenhouse gases, which also compromise your climate mitigation effect. So all these limitations and costs which are there leads to the fact that we need to build up SOC as efficient as possible. So we need to understand, and this is really the key of our research, which measures and soils are best suited to do that. And when I say efficiency, I mean a high SOC build up per unit of biomass, right? And this can be achieved when we feed this lingering carbon pool with a long residence time, which we already heard about, which we nowadays believe it's the mineral-associated organic matter pool, which is separated now into, well, mostly by size fractionation. So we also heard about the saturation concept. It's basically a concept of a bucket. If you fill this bucket with popcorn, then yeah, Francesca said it's a pizza. I say it's a popcorn bucket. When the bucket is full, the popcorn falls over and can be decomposed by your neighbors or whoever. It's not stable anymore. So, and following the saturation concept over time, it has been used to estimate the SOC sequestration potential of soils, and it has often been observed that there are oversaturated soils, because Hassing was coming from a correlation, a mean correlation with like cultivated, uncultivated and natural grasslands, and we've seen in cultivated and uncultivated soils that it can be much higher carbon in the minerals associated to minerals. And therefore, we have a new estimate, and these estimates are actually pretty similar in many publications. As outlined here, the recent estimate by Giorgio giving this upper line. So now it's not the mean regression anymore, it's the upper line, the upper boundary, implying that there's actually one specific C loading of the silt and clay fraction. So the slope of this regression is the C loading, right? I would like to hand over this value to you just keep it in mind, it's 8%. Yeah, 8% of the silt and clay fraction, according to this concept, can be stabilized by the minerals. And following this concept, following this upper line, we actually have no soil in the world. This is what Francesca mentioned, more or less, that is actually saturated. So especially in the agricultural areas of the world, we are far, far below the saturation limit. So the potential must be huge, the mineral potential. Now you can also access this as a function of total soil organic carbon. We've already seen that. You can do it at individual sites, which is difficult to do because you need a lot of input. And following the increase in soil organic carbon over time, you might eventually see that this mineral-associated organic matter comes to a steady state, or not a steady state, but it saturates and only POM accumulates. So this is difficult to do. So what you can also do is a multi-site comparison, multi-site investigation. And as Francesca already mentioned, this paper here was not meant to find a initial or a maximum capacity, an upper limit really, but this is how people interpret this. So people interpret this as, okay, there is no mineral associated organic matter above like 50 grams per kilogram. So it's basically an empty space here. This empty space is predicted. So we thought, okay, we are sitting on top of 15,000 archived soils, and let's see if this is also true, if this holds true for agricultural soils in Germany. So we went to our basement and selected some soils, and we didn't select them to represent Germany. This is very important, but we wanted to have, the whole range of SOC contents up to 12%, so 120 grams per kilogram. And then we wanted to see if there is something like a flex point if you include really the high SOC soils. We did a physical fractionation with a size cutoff at 50 micrometers and end up with this correlation here. So you see it's amazingly stable, especially in the croplands, how the MAOM actually, the proportion of MAOM of total SOC is really stable. And similar, it's for grasslands, but you see that the grasslands start to scatter up here. And you see by the size of the points, you can tell that, okay, it must be related to texture somehow, which also makes sense. But if you, this is like the same square. You see the square is not empty, but if you now plot this by texture group, you see that we still don't see any flex points. So the slope of the regression is differently. It increases with silt and clay fraction. So the more fine fraction you have, the higher is the slope. So the more is the proportion of MAOC. But also in sandy soils, you don't really see that it's leveling off. So it can become very high. And this is comparable to other results, to the results of other authors, like Matus in a global meta-analysis. And on the right side, it's a Finnish study on a very clay soil, but you see it's a very straight line, the relationship of MAOC and SOC. So for us, it was really surprising to see how stable this proportion actually is, and just keeps on increasing when you increase SOC. So you don't necessarily, and let's say there are just a few soils, as mentioned, that can go so high, or they are going so high actually, but there's no leveling off of mineral associated organic carbon as we define it here. We define it as the fraction smaller than 50 or 53 micrometer. So you can also turn around this data set, and now this C loading comes back into play. So what I show here on the y-axis is the C loading of the silt and clay fraction. So how high is the carbon content in this fraction? And then we correlate that against the amount of fine fraction in the samples. And as you can see, especially in the grasslands, so in the croplands is pretty stable, but in the grasslands you see there's a negative correlation. So carbon seems to accumulate in the fine fraction when there is little of this fine fraction. This is an interesting finding, I think. And if you plot this 8% line here, you see that it doesn't apply to all soils. It basically applies to the soils that have a lot of fine fraction, but there are many soils that don't have so much silt and clay that go well beyond this line. And this holds true when you put all these big data sets that we've been discussing together, like our data sets, the Giorgio data set, Lucas, and the Matus data set. You see that there are actually many soils where you can, both in croplands and grasslands, come beyond this 8%. I'm not saying that this is like totally directly on the mineral surface, but it's what we isolate as mineral-associated organic carbon. So it seems like the small buckets can accumulate a lot of popcorn on top of them, while it doesn't happen with the big buckets so much. And that is interesting somehow. And it means to me that the bucket size is not actually the ultimate limit to the accumulation of popcorn, so to say. And we should also keep in mind that actually the accumulation of mineral-associated organic carbon is patchy in the soil. So it doesn't happen like a homogeneous layer. It happens at specific hot spots where the surface is a bit rougher and things like that. As you can see here in the nanosims picture. And the interesting thing is that when you add new carbon to that, so they did a litter incubation, this new carbon actually ends up not at the free surfaces, it adds up where there's already a lot of carbon. So it is indeed something like a piling up that happens. That means, for me, it is just an indication, but it could mean that the MAOC formation is somewhat decoupled from the mineral surface area. Of course, a small bucket remains a small bucket. But the question remains, why are we actually not observing more fine textured soils with very high carbon loading? So you see this upper line here, this 8%, and you see in the lower area, there are a lot of soils that are actually overshooting this limit, while at the lower end, nobody's there, basically. Is that because of saturation, or is that, are there other reasons? And I think I would hypothesize that we just don't have enough input to reach that. And that is also not really a contradiction to what Francesca said. It's just, we will never reach that. I mean, just a rough back of the envelope calculation. Let's say we have a soil with 80% silt and clay. We want to be as high as 10% carbon in the silt and clay, so 10% carbon loading, which we see in the sandy soils. A bulk density of 1.2, 30 centimeters, that would mean 290 megagram per hectare of mineral-associated organic carbon. We say this fraction has a average turnover time of 100 years, which is already long, I think. So we would actually lose about 3 tons of carbon every year. And if we have a formation efficiency of 10%, we would need almost 30 megagram of carbon to keep that steady state. I hope you can follow. That is way up, way beyond what we actually have. So the carbon input of German agriculture is 3 tons. So that's 1/10. And if you look at a global NPP map, and let's see just the temperate region, we have 6 to 9 megagram of pure carbon per hectare. We would need 29 to actually come across this 8% line. So basically, in very high clay and silt soils, the major limit is the carbon input. And also, I mean, that's what we've shown. We see some soils that gain a lot of mineral-associated organic carbon, and those soils are probably those that have limited decomposition again. I mean, there are a few clay soils and stagnant soils in the data set, so it's either the input or the output, so you can screw on both. Right, so let's assume we have unlimited inputs. We go to the farm level. You're a farmer and you want to distribute organic matter over your fields. And you have to answer yourself a question, which is, okay, how can I have really the largest effect of my organic matter distribution, of my manure distribution? Where do I gain the most soil organic carbon? Is that spreading it all over all my fields, concentrating it on one field? Should I even care for the initial carbon content of my fields? And this was tested in this study here by Henrike Heinemann, 4 different long-term experiments that we sampled, and those received a lot of manure for quite a long time. So the upper 2 ones, they received for 37 years, 4 different amounts of manure. And the highest addition was 19 tons of carbon. So this is really crazy, but you find like long-term experiments about everything really. And so as you can see, in all 4 experiments, it looks like there's a linear increase in soil organic carbon stocks, which we might not really expect when we think that the soil is actually, you know, approaching its saturation limit. Then looking at these soils and looking at the initial MAOC content in the upper figure and the initial bulk SOC content, we see that actually there's a positive correlation of the carbon sequestration efficiency and the initial carbon in the soil. So I'm not sure if I believe that so far. If this is a general thing, I don't know. But we see here that actually there's not a negative correlation. So it doesn't negatively influence your carbon sequestration efficiency when you already have a lot. So this study points to me that there are huge amounts of carbon that can be added without soil being a limiting factor to build up more SOC. And the second thing is the saturation deficit doesn't seem to be relevant to estimate the sequestration efficiency of soils. And let me say that two of these soils, the upper two, which received a lot for a long time, are actually Chenu sands. So it's black soils with a lot of carbon to begin with. And here you see this is one side, and one is a bare fallow treatment, the lower one, and the other one is a crop rotation. And you see that you actually gain more carbon when you put a lot of manure to the crop rotation instead of the bare fallow. So this is really strange and a bit unexpected, but yeah. So let me come to the end. I think I have 3 to 4 conclusions to make. First of all, soils can have very high MAOC contents when the conditions are suitable. So, but in most cases, the carbon input is not high enough, or the carbon mineralization is too fast to reach these very high levels of SOC and MAOC. So when we first put this on Twitter, there was reactions like, oh, this is good news, but I think we shouldn't overinterpret this as good news. It's more like, well, there could be a theoretical potential, but this potential stays really theoretical. Second, MAOC formation is somewhat decoupled from available mineral surfaces. We see these sandy soils that can have very high carbon loadings. We don't really know why. The carbon is accumulating in clusters, so not homogeneously. So it's really hard to estimate an upper limit in such a system, I think. So I would say the general upper limit might be there, but it remains elusive. So we cannot really say where it is because we are limited by carbon inputs. And of course, a small bucket remains a small bucket. That means you can never be as efficient and as high in a sandy soil as in a soil with a lot of clay and silt. Third, the SOC sequestration efficiency is not necessarily lower in SOC-rich soils, which I've shown in the last slide. So we think that the saturation deficit is really not the appropriate measure to estimate the SOC sequestration potential of soils. So it's not if you are 20% or 40% saturated, you will lose efficiency. We're not seeing that so far, so we need more evidence for that. And models may not need a carbon saturation mechanism. I think the clay dependency is more important. And the third thing is as I already mentioned, more controlled experiments are needed to really get to the drivers of this sequestration efficiency. Yeah, and lastly, let's keep an eye on this high SOC soil. So this is a bit contradicting to what Francesca said. I don't think we should exclude them. We should really study them because they can tell something about mechanisms. They are hotspots. I mean, hotspots of potential losses, and we are facing a lot of losses of carbon throughout the world. So we should also not only focus on carbon sequestration, but also on loss mitigation. So that's it. Thank you.
Okay, thank you, Christopher. So if you have any questions or comments, you can put it on the chat box. So let's have a discussion. So we originally have Claire Chenu, who is going to lead the discussion, but unfortunately, there's a emergency that Claire can't be with us. But she did send some comments that she wants to ask both of you. So shall we have a discussion, Francesca and Christopher? So Francesca, you mentioned it briefly that there are different ways of separating particulate and mineral associated organic carbon in the literature. So there are different ways. Then some use dispersion, some use shaking, and so on. And also mesh size also different. Some use 20 microns, some use 50 microns. So so how do you see the next steps in so that we can make comparisons between these different studies and so that we can have a more uniform way that says that this is not due to the methods discrepancy and so on? Maybe first, Francesca, do you have any comment on that?
Yeah, indeed, it's very hard, and in my opinion, now. So I started with the size separation because it's the fastest, the quickest, the cheapest, and so when we have to do hundreds of soils, I went with size separation both with the Lucas and the NICS data sets. But as we completed that work. And actually, we were also trying. So the size separation, the point is that you need to disperse the soil, disperse the aggregates, and depending on the method that you use to disperse the aggregates, you end up breaking always a little bit more, a little bit less. Some of the particulate organic matter. And so when you then separate it by size, that particulate organic matter ends with the mineral associated organic matter, in addition to also the dissolved organic matter, because the size separation collect everything into a bucket. And so into a sieve. And so at the end with the size separation, you do have contamination of MAOC on top of not having distinguished the mineral associated MAOC to the organic carbon bond binded to the MAOC. So those are two problems. So you can be more finer in your work, really identify a dispersion method that breaks the POM the least, which is hard to find the same method across so many soils. And that's the other problem we have when we work at large scale, that different soils, particularly, Christopher used the ultrasonic, then the same energy have very different dispersion depending on the soil you use. So that's why we use, for example, mechanical dispersion. That is supposed to be a little bit more standardized, but no method are perfect by any means. The density, we find that separate is slightly cleaner MAOC with less thing. It's more more tedious, it's more costly, and so we are trying to define a way to increase throughput. For example, by combining density separation with FTIR modeling, and that's how we think. I think that if at global level we manage to have the same way of separating, even if none of them might be ideal, at least we are comparing apple with apple, because it doesn't, I'm not convinced that those few high-level carbon soils actually have a very cleanly separated MAOC, or don't have a ton of organic carbon piled up on which is a question. So I'm totally I'm sorry if maybe I was misunderstood. I don't want to say that we don't have to study the high carbon. So actually we have to study them to understand the mechanism, why there is so much carbon there, but we cannot assume that every soil can get to that point. That was my point. And I think Christopher and I actually agree. We just, and it's fun like to debate. I don't think that we totally disagree on this issue. We just come from slightly different viewpoints.
You have comments, Christopher?
Yeah, I mean, your original question was in the direction of comparability between, I think, yes, different dispersion methods and labs and so on. And well, this has always been an issue in the whole fractionation history, and also the issue that we're not separating really, homogeneous or clear fractions chemically or also functionally. So it's always a mix. And of course, when you go down to 2 fractions, there is quite a mix, because it's only 2. You know, we're coming from like 7 or 9, which is interesting, which has revealed many interesting things. But I think it was a clever move from Francesca, to be honest, to go down to these 2 fractions, because they are different and we learn something when we isolate them. And now we have the chance to bring it all together in global meta-analysis and study really patterns. You know, this was really not possible before. I think everybody was happy to see that they only have to isolate 2 fractions now, if Francesca says so, Jocelyn in this case, we do it, and everybody's doing it. And now we have big data sets, and big data sets always have an advantage. But of course, we have to be careful what we compare there. I am maybe a little bit less critical than Francesca when it comes to the dispersion method. In my experience, if you use glass beads or ultrasonic or whatever, the results didn't differ so drastically, at least from the total amounts of carbon that end up in each fraction. So it's, for me, of course, density and size is something different, but like the dispersion method was, in our experience, relatively comparable.
Okay, thanks. So there's another question from Claire. So we know that this is POM and MAOC is operational, and I think it's as I first heard it from Francesca in 2019 when she presented in Adelaide. I think that's great that we simplify things, but sometimes we know that the MAOC itself is not homogeneous, and so also that the residence times are not homogeneous, and people tend to oversimplify things. So, and some people say that I read on something that people say that it's focusing just on MAOC is overrated. So, how do we deal with this? Are we oversimplifying things, or are we focusing too much on one thing?
Yeah, so I was actually astonished by how much the community responded to kind of the invitation to simplify. I think that opinion came at the moment in which I was frustrated by some synthesis done with total carbon. And that to me was more frustrating than the synthesis done with the 8 fractions, right? So I was trying to say we cannot really, the total carbon behaves as a weight average of 2 very different things, or more different things. And so I think we cannot come, we will not advance much our understanding if we keep working on total carbon. I knew, because I work actually, Christopher led a very interesting work for all of us across the world, saying, guys, we cannot, particularly if we want to do global studies, we cannot do the very complex fractionation. It's not doable on hundreds and thousands of samples. And so we had to simplify to try and make a step ahead. I am impressed by how the community has responded to that, and by how big a step we have made in understanding soil organic matter by just doing this simple fractionation, as Christopher said. But now we have made that step. So I feel that's what I'm doing now in my lab. I'm going farther than POM and MAOC. I'm actually a little bit like bored of that. Is okay, we learned so much. Now what are the new questions? To me, the new, or sometimes even the older question is like, I'm now finding with isotope that MAOC, which is something that has been identified before, but like when the MAOC form inside microaggregates actually has a lower carbon to nitrogen ratio, is more microbially derived, whereas the MAOC that is free have more of the plant exchange from DON. That's what we are kind of hinting to. And so, yes, now I feel like we have learned a lot. So I'm very impressed by us as a society of how we came together and really advanced knowledge. But this is time to move farther. This is the time to understand this MAOC is very heterogeneous, both because of our limitation in separation, and also because we still don't know how to separate the organo-organoid MAOC from the OC MAOM and understand whether they have different stability. It's done at the nanoscale. We need to do at the thousands of samples, and we are still not able to do that. So those are very important questions, and I'm now saying to the community, let's move on. We have learned a lot, it was great. Now let's go more into more details.
Christopher, do you have anything to add?
Yeah, no, I mean, I agree to many of the points said, and I think that maybe even the POM heterogeneity is even higher than MAOM. And yeah, it's no wonder that we're seeing more POM in forest soils, for example, and I still don't really know how we can manage specifically POM or MAOM. I mean, if you add only straw, this is pure POM, but you're not managing the POM pool because the straw is gone in nothing. So what are we actually, I mean, it depends on the question, right? And if you have only two fractions, there are many questions that you really cannot answer. And also in the mechanistic, yeah, if you want to proceed mechanistically, this is not enough for sure. It's nice to see these patterns and to combine it also with other measurements. You can, after you've isolated your fractions, you can do whatever with them. You know, you can quantify amino sugars in MAOM or do many things with them. But just looking at these two fractions, yeah, it comes to an end. And we're having a lot of data, and we're using this data. Probably a few more papers, nice papers will come out, but maybe it's also time for moving on, and maybe not.
If I can add one thing to what Christopher just said, is that I was shocked by my student could explain only 30% on the variability on the stock of MAOM and POP from input, climate, and texture. So, you know, even the input, we need to understand really, is it the mycorrhizal? What is it that the soils don't sequester more carbon? Even, you know, the natural soils. Yeah, input might be limited, but it's not the only thing.
Okay, I think related to that, I think Francesca, you touch about it as well. So at the moment you're defining this saturation, is it mainly physical, or do you also consider the environment that is, for example, in the Hassing paper, the 97 paper, he excluded two of the Australian soils because the carbon level is lower than other regions in Europe, because here in Australia the rainfall is lower, and so we got a high. So for example, in Australia, although the physical capacity we have for the physical capacity, but we will never have the biomass capacity, as Christopher mentioned in your talk, that we will never have the capacity as for example in Europe and the US, where you got wetter or more biomass climate. So are you talking about the physical limitation or also environmental limitation?
Yeah, and I think that both Christopher and I have pointed to this in our talk. So there are the coarse textured soil, the one with very little capacity. They are almost, you know, they can get to a physical saturation in environment where they receive enough inputs and the climate support the stabilization. But the fine textured soil, the physical limitation imposed by silt and clay is not really of concern at this point. And there are, you know, input limitation, climate limitation, and what I was saying before, limitation of our knowledge gap. It's not just climate and input. There is something else, whether it's microbial, whether it's the interaction with aggregates, inside aggregates will be myoma associate proportionally more. Those are all the open questions, but I would really kind of separate the question. That is also what, Virgile does in her study, which at the low silt and clay, actually, and also the medium, the polynomial fit better than the linear. So those soils, they can reach saturation, and we need to point that to producers that have those type of soil. But a ton of other soils are much more much more environmentally limited or limited by our knowledge to increase carbon. And one thing we haven't touched on is that actually a lot of the relationship with silt and clay, we need to force to zero. If we just plot a line, it will have an intercept. And that's another question that we need to address. And so why a low silt and clay stabilize that much carbon? And maybe understanding those mechanisms can increase our potential to sequester carbon across the range.
So there's a question here, like especially in regions, for example, in Australia or other areas where they have a high fire. So should we also consider pyrogenic carbon to separate out from the MAOC and POM? Maybe Chris, can you?
Yeah, of course. I mean, this is a fraction that has a very, very different stability in the soil, but it's super hard to do. We all know that it can be in the POM or in the fine fraction. It can be everywhere, and it's very different regarding its stability. But yeah, it's actually not so different regarding its chemical because it's carbon in the end. It's different, and it's not like a specific carbon. So it can be many things. So it also like chemically to really find the proportion of biochar in the soil is challenging as far as I can see. So it's not so easy, and yes, if possible, we should try to, especially in those soils that are fire affected, we should try to quantify that. But I know that people are struggling to do so, and we're still finding the best method to do so. And of course, you can also visually try to pick out the charcoal and stuff like this. Tedious.
So another question from the chat, that if from Sean Saleh, is that if we can only manage the system to a steady state because either water limitation or low input, so how do we identify and communicate those to land use specific conditions?
So the majority of the soil are actually even below that actualized capacity. So let's say there is a physical capacity, there is a capacity that can be met by environmental thing, and the majority of soils are actually much below that. So I think there is a large space for increasing soil carbon. We need to provide context-dependent management advices and suggestions to maximize that capacity, depending again on the type of soil and the mineralogy and the climate, and of course the socioeconomics of the producers that can do something but cannot do other things. So it's a mixture of things, but the potential is high as we have shown. And so I think us scientifically, it's very important that we understand those mechanisms. But I agree that this shouldn't worry people wanting or thinking that we can increase carbon in soil. We have lost a lot of carbon from our soil, and that potential is definitely there to be reached again.
Okay, so there's one question from Claire to Francesca. She said that, could you define the paleoclimatic domain for the validity of the saturation approach? Because I think in one of your comments in the paper, you said that hydromorphic soils and of course organic soils should not be of a concern. So are there criteria that you want to define upfront that this saturation should be applied into certain condition? Or
I mean, the saturation concept applies strictly to mineral associated organic carbon, so not to total carbon. Then total carbon can find a plateau for a number of different reasons, but the saturation concept only refer to the organic carbon that is binded to minerals. And so when that is the mechanism for, that's not the mechanism for stabilization of carbon in wetlands or, you know, in organic soil. Those accumulate carbon because of environmental constraint, lack of oxygen, temperature, or other things. So it's a matter of definition. Yeah, it only applies to the mineral associated organic carbon, which means the carbon directly binded to OC. It doesn't even apply to the organic carbon binded to organic carbon, which is binded to OC, even if we can't make that separation. But the concept is only for that component of soil.
okay, thank you. So Chris, do you have anything you want to add, or do you have anything you want to ask Francesca?
You should ask me for a beer out. I mean, after all the time.
Not before your breakfast, no. I mean, I agree to a certain extent that we should, you know, be careful what we consider MAOC if we just do a size fractionation and we call it MAOC in the moment that we have it smaller than 50 micrometers, which is certainly not 100% the case. The question is, what would be the best method to really get to the point that we remove all the stuff that is not directly, you know, associated to the minerals. And we used to do that with chemicals, for example. We really burn off the whole stuff and see what is left. And that is really like the stable stuff. Is that still something that you would think we should do? Or because when we go to a density fractionation and remove all the floating fine palm or the organo associations somehow, then yeah, we will also get a mixture again. We get minerals floating and things like that.
We discuss this every day in my lab. We don't have an answer. It's also, the point is, how do we separate the organo from the organo-mineral? And does it matter? You know, is it true that the organo is less stable than the organo-mineral? That we don't even know that. So that's I think I was trying to make that point. We have that information from nanosims, but another very high tech, low throughput, highly costly analysis, but we don't have a method that we can do a scale. And that's one of the question we ask constantly in my lab. So if you do find that method, let me know, because we are in search of it.
Okay, I think we have enough discussion, and I think Christopher needs to have a beer, and Francesca needs to have a breakfast. I need to go have some sleep. But before we go, I want to ask Francesca. So, on your CV, it says that you become an entrepreneur and co-founded with 5 other women, Sequester Analytics. Can you tell us about it?
It's just a service lab, so I actually care a lot for research, and I ended up having too many requests for service in my lab, in my research lab. And my CSU testing lab, they do testing for nutrients and stuff, and they didn't want to go into carbon. And so I proposed my collaborator, you know, do we want to start just a lab, a service lab to do in the other, you know, I don't want to speak badly of the other lab, but there are a handful of labs in the world that know how to do carbon. there has been immediately a huge request for carbon analysis and fraction analysis, but we have this know-how in our research lab, and the service lab don't have that know-how, and they thought that they could apply the same processing, pre-processing of soil that they do for ag soils when there are no roots, no stones, and they just measure cation exchange capacity or nutrients or stuff like that to soil carbon. And so I noticed a need by the industry and by even colleagues that and I didn't want to occupy my research lab with service. And that's what motivated, and it's actually been fun. There are like 10 kids working in the lab, and we started with the garage mentality. And I idly, I don't work there. I work full time at CSU, but the lab is actually thriving.
Maybe one follow-up question. So I mean, there are lots of interest, of course, for soil carbon sequestration, but so should we measure those two fractions that for carbon sequestration? Should we focus on the MAOC?
I think that we need to model fractions that have different mechanisms of stabilization and persistence if we want to provide good forecasting of management of climate change effect on soil carbon in the next 10, 20 years. I think that if we only, so today there is carbon with the same age in soils for different reasons. And so if we use models that define carbon by their age or by their Thünen over time, we might have faulty responses moving forward because one type of mechanism might be affected by climate, but not another, or by management, but not another. And so to me, it's important that we have decision support tools that represent this concept correctly. And of course, if we want to have a robust decision tool, we need to have enough data for their robust calibration and validation. And so I'm not saying that that a farmer need to measure palm and MAOC just to know it. But until we develop robust decision tool, we need these measurements to inform our science, develop the best tools, and calibrate and validate them. Once we are there, maybe we can go more soft. But again, we also need to be able to increase throughputs. And I think that physical fractionation coupled with FTIR, coupled with artificial intelligence can really help us move into scale. But as a community now, we should try to at least use the same method for the basic physical work, and then we can use this upscaling in a more coordinated way.
Okay, thank you. Chris, do you have, what is your current venture? What are you doing at the moment?
What I'm currently doing related to fractions. Well, I'm sitting in a webinar. No, but actually regarding the fractions, I mean, we're actually approaching this high throughput thing by these two fractions a little bit, and we're combining it with drift, for example. So mid-infrared spectroscopy. We're combining it with rock eval in a project. We bring together from many continents and many monitoring networks actually samples, also trying to find transfer functions to compare those different protocols, but then also compare that to rock eval fractions. And that is interesting. I mean, I don't know if you've followed that, but this is another way to actually distinguish between stable and labile organic matter. It involves rock eval on the one hand, but a machine learning model on the other hand, built on long-term bare fellow experiments. So it's an interesting approach to compare those two and see if they actually are redundant in a way, or if they are giving different results. So this is something to look at. And yeah, I mean, when it comes to really mechanisms and processes, and so I agree, 2 fractions is maybe not enough. But on the other hand, informing farmers, like what is the best management to manage your soil and to increase carbon, 2 fractions is maybe too much already. because as I said, I mean, name it too far away from the saturation level, or name it, yeah, you can increase carbon. You don't need this information, how much POM and MAOM you currently have to really manage your land, I would say. Not so much. It's more like when you want to predict, maybe will you lose carbon in the future? So you know, if we're having more MAOM, then we are maybe less likely to lose carbon than when it's more labile, the whole thing. So I don't think we need it in all cases.
Okay, thank you, Francesca. Thank you, Christopher, for your presentation and your time, and thanks everyone for joining us. And before we close, and as we mentioned earlier, said this is just the beginning of this is the first series, and we have another webinar coming on next month, on October the 17th. We have a webinar on soil inorganic carbon. So we talk a lot about soil organic carbon, but there's the other half of carbon that we really less talk about. So that's soil inorganic carbon. We have Kazem Zamanian and Inigo Quesedo will talk about that. And in November, we are going to have another webinar. This is on the issue of measuring, reporting, and verifying soil carbon sequestration. Should we measure it or should we model it? So we got Pete Smith from Aberdeen, and also Alex McBratney from University of Sydney, who will discuss this topic with us. So please stay with us and keep coming. Watch out for this workshops. And sorry today that we have reached the maximum capacity, but the recording will be made available soon by maybe the Secretariat. And thanks for your time.
So the webinar was saturated.
Yes, the webinar is saturated.
No, it was a mistake from us. We will solve that problem next time. Thank you very much to all participants to our distinguished speaker. Bye-bye.
Thank you.
Bye.
Thank you. Bye.